video for the next lecture. Okay. Okay. So this is on chemical equilibrium. Okay. Okay, I try to increase the slide a little bit. Okay. Bismillahirrahmanirrahim. Okay. The concept of equilibrium. Do all chemical reactions go to completion? Is a question. Okay. So when you start with only reactants, do you end up with only products? So if you start any chemical reaction, at the end of the day, do you have all the products, or do you have mixture of the reactants or and the products? Okay, it's a question. Okay, most of chemical reactions are reversible. Okay, meaning that you have a forward reaction and you can also have a reverse reaction. They do not go to completion. Okay, meaning that not only the products present there, there could be some reactants also in the reaction mixture. In fact, they will be left at some instance with a mixture of reactants and products which are in equilibrium. Okay, their concentration are not changing. So, at a certain time of the experiment, okay, we could have a mixture of both, okay, reactants and products, and they are in equilibrium. Okay, at equilibrium, the concentration of the products and the reactants are not changed. At equilibrium, the concentration does not change. Okay. So that's the concept of equilibrium. Equilibrium, basically we have um, reversible reaction. Okay, and then and any at any point of the reaction, okay, we could have both the reactants and the products. So that is the concept of equilibrium. So you can see the graph here. This is rate of reaction versus time. Okay, if we increases time, okay, the forward reaction, the rate for the forward reaction increase. Okay, you can see that is increasing. Okay, and the rate for the reverse reaction decrease. Okay, increase in time, the rate for reverse reaction decrease because it wants to form the products. Okay, and it will come to a point where it reach equilibrium. This point. Okay, as the system approaches equilibrium, both of the forward and reverse reaction are occurring. So both happen, the forward and also the reverse reaction. At equilibrium, the forward and the reverse reaction are proceeding at the same rate. At this point here, equilibrium state, the forward reaction and the reverse reaction, these proceed at the same rate. Okay, this is a chemical equilibrium and reaction of N2O4 gas, which is dinitrogen tetroxide, okay, in equilibrium with nitrogen dioxide. Both are gases, okay. So the gases are in a vessel. Okay, Kf is a equilibrium constant for the forward reaction from N2O4 to form NO2, and Kr is the apa ni, Kr is the constant reverse constant for the reverse reaction for the formation of N2O4 from NO2. Okay, as time passes, more NO2 is produced and the brown color intensifies. If we increases time, okay, look here the time, okay, the forward reaction, NO2 formation increases. And after some time, the brown color stop changing. So the brown color indicates the formation of NO2. And the more NO2, okay, the brown color intensify, which means that we have more NO2, means that the concentration of NO2 increases over time. Okay. After some time, the brown color stops changing. The concentration of NO2 become constant. So NO2 at this point it becomes constant and the color does not change anymore. Same does with the concentration of N2O4. N2O4 also, we have constant concentration. Okay, so at this instant, does the reaction stop? Okay, so we try to understand that. Okay, the reaction is actually reversible. We have a reverse reaction, which means it does not stop, but it proceeds at both directions. The reaction is reversible. Okay, it's not irreversible. Irreversible means it goes in one direction. Reversible means it goes in both direction. So we have here, okay, rate of forward reaction which is equals to rate of backward reaction. So it's reversible. So in this case, dynamic equilibrium is established. Okay, the reaction does not stop. It continues running on both directions at equal rates. So the reaction does not stop, but basically they are all occurring. The forward occurring, the reverse also occurring at at equal rates. Okay, so the rate for forward reaction can be denoted as Kf times concentration of N2O4, and the rate for the backward reaction is K times concentration of NO2 to the power of 2. Okay. Okay, so as we speak just now, okay, we talk about the reversible reaction between N2O4 and NO2, and we have established equilibrium here at this point. The rate for the forward reaction change over time. The forward rate gradually decreases. Okay, this is the forward reaction. The rate gradually decreases while the backward reaction gradually increases. Therefore, at equilibrium, both rates becomes equal. So at equilibrium, we have equal rates of reaction. I think increase back. Okay. At equilibrium, the rate of the forward and reverse reactions are equal and the concentration are constant. We have a constant concentration. The equilibrium constant KEQ is a value. Okay, KEQ is a value representing the unchanging concentration of the reactants and the products in a chemical reaction at equilibrium. So we have concentration at equilibrium which is constant, and we can calculate KEQ if we know the concentration of all the reactants and products at equilibrium. Okay, for the general reaction, in order to calculate, we need to have an equation, kan? So for a general reaction between A plus B to form C and D, so this is a reversible reaction. We have A reacting with B to form B, C, and D, and we have small a, small b, small c, and small d. These are the stoichiometric coefficient, or the number of moles of the reactants, A and B, the number of moles of the reactants, while C and D are the number of moles for the products. So at a given temperature, KEQ, the equilibrium constant, equals to concentration of C to the power of C times concentration of D to the power of D over concentration of A to the power of A, concentration of B to the power of B. So A, B, C, D, big A, big B, big C, big D. These are the concentration of the reactants and species. Okay, the nominator C and D, these are the products. Okay, denominator A and B, these are the reactants. And small a, small b, small c, small d, these are the stoichiometric coefficient, or the number of moles of the reactants and products. Okay, let's take for example the reaction between hydrogen and nitrogen to form nitrogen ammonia, okay, NH3, or nitrogen trihydrogen. So 3 moles of hydrogen react with 1 mole of nitrogen to form 2 moles of ammonia, okay, and this reaction is in equilibrium. So KEQ for this reaction equals to, okay, KEQ for this equation equals to concentration of NH3 to the power of 2 over concentration of H2 to the power of 3 times concentration of nitrogen to the power of 1. Okay, hang on. Okay, so in order to derive, okay, to get the KEQ, the chemical equilibrium constant, the equilibrium constant for this reaction of nitrogen and hydrogen to form ammonia. Okay, so we can write the concentration of nitrogen to the power of 2 because the number of moles of ammonia to the power of 2 because the number of moles of ammonia in this equation is 2. Okay, over the concentration of hydrogen to the power of 3 because the number of moles of hydrogen is 3 times the concentration of nitrogen to the power of 1. Okay, 1. We don't write 1 there, but it's 1 there. Okay, so basically equilibrium constant is we take the concentration of the products, okay, over the concentration of the reactants and the power to its number of moles or stoichiometric coefficient. Okay, for this reaction, we have ammonia reacting with oxygen in equilibrium with nitrogen plus water. In order to write down the KEQ, which is the equilibrium constants for this reaction, equals to, okay, nitrogen, concentration of nitrogen to the power of 2 times concentration of water to the power of 6, okay, because we have 6 there, over concentration of the ammonia to the power of 4, okay, because number of moles of ammonia is 4 times concentration of oxygen to the power of 3. So in order to calculate KEQ, we need to have the values of the concentration of the reactants and the products. Okay, if we have all those information, then we are able to calculate KEQ, and the concentration should be at equilibrium. Okay. Now, the magnitude of an equilibrium constant indicates the extent to which the forward and reverse reactions takes place. The larger the equilibrium constant, the farther the reaction is the reaction at equilibrium. So what does it mean? Let's look at this equation. We have H2 plus I2 in equilibrium with 2Hi. H2 is hydrogen reacting with iodine to form 2 moles of hydrogen iodide. So KEQ is the equilibrium constant, equals to concentration of hydrogen iodide to the power of 2 over concentration of hydrogen times concentration of iodine, which is equals, in this case, equals to 54.8 at high temperature of 4 to 8 degrees C. So at equilibrium, more reactants than products exist. Okay. Now, for reaction of COCl2 in equilibrium with CO and also Cl2, KEQ equals to concentration of CO to the power of 1 times concentration of Cl2 to the power of 1 over concentration of COCl2 to the power of 1. This is equals to 7.6 times 10 minus 4 at temperature of 400 degrees C. Okay, the value for KEQ or KC, okay, the magnitude of the equilibrium constant. Okay, so if KC or KEQ is very large, okay, the reaction goes to completion. The equilibrium mixture will consist predominantly from products. So if you have really high KEQ value or KC value means more products exist in the reaction vessel. Okay, the reaction could have gone to completion. Okay, if we have KC or KQ, which is very small, the reaction does not occur to any significant degree. Okay, and most predominantly, okay, the reactants, okay, exist in the mixture. Okay. if the value of Kc is neither large or no small. Now, the reaction occurred to a significant degree but not to completion. The equilibrium mixture will have both reactant and products in comparable quantities. Okay, so we have both uh, reactants and also the products if the K is Kc or Keq value is not large or small, it's in between. Okay, magnitude of equilibrium constant Kc or Keq 10 minus 2 and lower, that is considered as small, very small. The reaction will not almost not occur. In between 10 minus 2 to 10 power of 2, the reaction will have an equilibrium which are both reactants and products. So in this case, in between we have both reactants and products. If Kc or Keq greater than 10 to power of 2, the magnitude is very large. The reaction will go almost to completion. So we have mainly the products. Okay, we can write equilibrium constant for many types of chemical processes. The equilibrium may represent number one, dissociation, acid base or solubility, formation of products, complexation reaction, okay, redox reaction, distribution between two phases, water and non-aqueous phase. So equilibria, actually there are several types of equilibria, okay. So this one you will go detail later on. Okay, for acid-base equilibria or acid-base dissociation, we represent equilibrium constant as Ka. Okay, let's look in Ka. Okay, here Ka. Solubility Ksp, the equilibrium constant. Complex formation Kf, formation constant. Keq, redox reaction. Phase distribution Kd, distribution coefficient. So equilibrium constant, okay, there are several types of equilibrium constant. In this case, we have one, two, three, four, five, five types. Okay, Le Chatelier principle. If a change is imposed on a system at equilibrium, the system responds by shifting in the forward or the reverse direction that minimizes the effect of that change. As a result, a new equilibrium position will be re-established. So the Chatelier principle deals with the change of the equilibrium. Okay, the equilibrium can change or respond towards shifting in the forward reaction or backward reaction or reverse reaction in order to minimize the effect of that change. Okay, if we put some change to the reaction mixture, so the equilibrium will move either to the left or to the right to reduce the effect of the parameter of that parameter. Okay, and because of that, a new equilibrium is re-established. Now, for the reaction of 4NH3 plus 3 moles of O2 in equilibrium with 2 moles of N2 plus 6 moles of H2O. We have KEQ, which is concentration of nitrogen to the power of 2 times concentration of water to the power of 6 over concentration of ammonia to the power of 4 times concentration of oxygen to the power of 3. Okay. The magnitude of an equilibrium constant, okay, the value of Keq or Kc, that indicates the extent to which the forward or reverse reaction takes place. The larger the Keq or the Kc, the farther the right is the right reaction at equilibrium. So if you have a really high Keq or Kc, means it prefers, okay, or predominantly more products are formed in the reaction mixture. Now, KQ for H2, hydrogen reacting with iodine to form 2 moles of hydrogen iodide. Okay, KEQ is concentration of Hi to the power of 2 over concentration of hydrogen times concentration of iodine, which is equals to 54.8 at 425 degrees C. Okay, so at equilibrium, more reactant than product exists. Okay, we have another example there. For the above, okay, I think we have gone through this. Okay. When when change is imposed on a system at equilibrium, okay, the system react in direction that reduces the amount of change. So this is the Le Chatelier principle just now. Okay, maybe I've just went to the wrong slide just now. Okay, so let's go straight on. Let's proceed straight away. Okay, so Le Chatelier principle. Okay, the system respond by shifting to the forward or reverse direction to minimize the effect of the change. Okay, and as a result, a new equilibrium is established. Now, if we have here, this shows that this is an equilibrium. We have the same amount of the one on the left and on the one on the right hand side. Now, if we put something more on the left hand side, so this is not equilibrium. It's not balanced, okay? So when a change is imposed on a system, the system will react in direction that reduces the amount of change. Okay, try to reduce the amount of change. So a change can be effect of concentration, effect of pressure, or effect of temperature. For effect of concentration, it can be removing the reactant of the products or adding the reactant of the products. Okay. Effect of pressure can be the change in the volume and pressure of the system. This only related to the gaseous reaction. Okay, gaseous reaction. Kalau reaction dalam bentuk liquid ataupun liquid or solid, this does not apply because the change of the volume and pressure only apply to the gaseous reactants and products. Change in temperature, okay, effect of temperature, effect of increasing or decreasing the temperature. Now, okay, so for effect of concentration on equilibrium, for most reaction, the rate of reaction increases as reactant increases. Okay, the rate of reaction increases if we increase the reactant. An equilibrium is disturbed when the concentration of one or more of its components is changed. As a result, the concentration of all species is changed to get a new equilibrium. Okay, to get a new equilibrium mixture, and uh, because of the addition or removal of a certain concentration of the reactants or products, therefore the mixture re-establish its equilibrium. Okay, now if we increase in products, okay, if we increase, so this is if we have a plus b to form c and d. Okay, and we have equilibrium, um, we have forward, we have reversible reaction. Okay, so if we increase in products, which means the c and d, so the equilibrium shift towards the left, towards reducing the products. Okay, now decrease in products, if we reduces if it reduces the product, so it will shift to making more products. So the equilibrium shift towards right. If we increase reactant also, that will increase the product and equilibrium shift towards the right. If we decrease the reactant, now if we decrease the reactant and the equilibrium shift towards the left, towards making more reactant. Effect of concentration change on the chlorine water equilibrium. Now we have this reaction, Cl2 chlorine plus water, 2 moles of water to form HOCl aqueous plus H3O plus Cl minus aqueous. Now if we decrease the concentration of Cl2 and H2O, okay, and also decrease the concentration of H3O. Okay, if we decrease the concentration of Cl2 and H2O, and also if we increase the concentration of Cl minus, H3O minus, that will shift the equilibrium to the left. Okay, shift the equilibrium to the left towards producing more Cl2 and H2O. Okay, for pressure on equilibrium. Changes in pressure significantly affect the correction rate only when one or more of the reactants or products is a gas and reaction is run in a closed container. So there are two requirements there. Okay, the change in pressure it can affect the reaction if if we have one or more of the reactant or product is a gas. That is the first requirement. The second one is the reaction must be run in a closed system or closed container. If the reaction is not run in a closed container or in open system, so we do not have this effect, the change in pressure, because the gases it can just escape. Okay, in an open system, the gases can escape easily. Now, the effect of increasing the pressure is to increase the concentration of any gaseous reactants or product. If we increase the pressure, that will increase the concentration of the reactants or product. In a system that composed entirely of gases, an increase in the pressure of the container will cause the reaction and equilibrium to shift to the side that contains the smallest number of molecules. Okay, what does it mean? Let's have a look here. A decrease in the this is a volume. Okay, we can see a more example after this. A decrease in the volume of a reaction vessel will cause a shift in the equilibrium in the direction that minimizes the total number of moles. An increase in the number of reaction vessel, the an increase in the number in the volume of a reaction vessel will cause a shift in the equilibrium in the direction that maximizes the total number of moles. Okay, the change in pressure and volume. If we increase the pressure, okay, increase in pressure, the equilibrium will shift towards the side with the lowest number of moles. Okay, so we need to add the together the number of moles, which means the reactants number of moles have to add up together. The reactant number of moles have to be add up together. Decrease in the pressure that will cause a shift in equilibrium towards the side with the most moles. The increase in the volume that will cause the shift in equilibrium toward the side with the most moles, the most number of moles, and reducing, okay, decrease in volume that will shift the equilibrium toward the side with lowest number of moles. Okay, what does it mean? Let's look at the case here. We have nitrogen plus 3 moles of hydrogen to form 2 moles of ammonia. So number of moles on the left hand side for the reactor is 1 plus 3, which is 4. The number of moles on the right hand side is 2 mole. Okay, so this is 4, this is 2. And 2 times 6.02 times 10 to the power of 23 is 241 times 10 to 24 molecules on the left hand side. And the right hand side, we have 1.2 times 10 to the power of 24 molecules. Equilibrium will shift to the right towards fewer molecule, lower number amount of molecule if we increases the pressure. So this is higher number of moles, this is a lower number of moles, so it will shift to the right because right has a lower of fewer molecules. Okay, if we increase the pressure for this reactant, for this reaction, we have nitrogen reacting with oxygen to form 2 moles of NO. So let's look at the one on the left-hand side. We have 1 mole plus 1 mole, so that becomes 2 moles, okay? Total number of molecule is 1.2 times 10 power of 22 because 2 more times 6.023 times 10 power 23. So we have there 1.2 times 10 power 24 molecules. On the right hand side also we have the same number of molecule. Therefore, in this case, the equilibrium does not change. Number of molecules is the same for both sides of the reaction. For the reaction of NH3 plus 3O2, we have 2 moles of N2 plus 6 moles of H2O. So the KAQ is as shown there. Okay, the magnitude of an equilibrium constant. Okay, something wrong happened there. Okay, we are at there just now. So we have understand about this. The equilibrium does not shift. Okay, it does not shift. Okay, because the number of molecules are the same on the left hand side, same with the right hand side. Okay. Now, effect of temperature on equilibrium. When the process is endothermic, endothermic means we provide heat to the reaction mixture. The forward or the left to right reaction is increased. So it wants to form more products. When the process is exothermic, the reverse right to left is increased. Okay, when the process is exothermic, heat is being removed. Okay, so the reverse process is increased. When the temperature of the system is raised, the rate of the reaction increases. When the temperature is of a system is increased, the rate increases. In a reversible reaction, the rate for both the forward and the reverse reaction are increased by increase in the temperature. Now, heat may be treated as a reactant in endothermic reaction. Endothermic reaction, it wants to be heated, and if we supply heat, then that will actually shift the equilibrium to the right. For example, we have carbon reacting with CO2, carbon reacting with carbon dioxide, and supply heat here. Then before we have 2 moles of CO, 2 moles of carbon monoxide. Unlike the case with concentration and pressure change, the change in temperature of a chemical reaction can change the value of a equilibrium constant. Okay, this one temperature can change the equilibrium constant. It makes the reaction faster or slower depending on the enthalpy changing H accompanying the reaction. So temperature, of course, if you this you can relate with the physical chemistry that you have learned last semester, especially for the chemical process and the biotech students. Okay, you have learned about this. Okay, the heat, the enthalpy change. Okay, um, the enthalpy change, the value for the enthalpy change is different for at a different temperature. Okay, and the KEQ. Okay, KEQ, the change in temperature can change the value of KEQ, the equilibrium constant. Okay, so N, for example, N2O4 in equilibrium with 2NO2, okay, delta H is 58.0 kilojoule per mole. So let's apply the Le Chatelier principle to the heat absorbed by as a reactant. Adding heat means that reaction will shifted to the right. We add heat and we have more NO2. Also, addition of heat means an increase in the temperature. Addition of heat means we try to increase the temperature for the reaction. Okay, in this case, we will try to form more NO2. In general, increasing the temperature of endothermic reaction shift the reaction to the right, while decrease the temperature of endothermic reaction shift it to the left. Okay. So also this is another this is the same one lah, N2O4 in equilibrium with NO2. Okay, heating caused the change in the color from yellow to brown because there is change in the amount of NO2. Now consider the following exothermic reaction. This is endothermic reaction. So this is an exothermic reaction. If we have a blue. Okay, in the middle here we have COCl4 and cobalt carbohydrate. Okay, we have COCl4 and carbohydrate ions at equilibrium. If we heat up the system, so we change to blue, it will have COCl4 to minus. But if we reduces the temperature or cool it down, we have a pinkish color which indicate the presence of cobalt, hydrated cobalt. Okay, CO in a bracket H2O to the, okay, close bracket 6 2 plus. The increase in temperature favors endothermic reaction. The decrease in temperature favors exothermic reaction. So the change in temperature not only affect the equilibrium position, it also affect the equilibrium constant. Okay, so increasing temperature, okay, for endothermic reaction, K decreases. Okay, for exothermic reaction, K increases, and decreasing temperature for the endothermic reaction, K increases, and for exothermic reaction, K decreases. Okay, effect of catalyst. A catalyst is a substance that influences the rate of reaction and can be recovered essentially unchanged at the end of the reaction. A catalyst does not shift the equilibrium of a reaction, it affects only the speed at which the equilibrium is reached. So a catalyst is a substance that we can influence the rate of reaction, and we can add to the reaction to speed up the reaction. Okay, it can expedite the reaction to which the equilibrium to attain to attain the equilibrium faster. Okay. Okay, let's look at this diagram. We have potential energy versus progress of reaction. Energy diagram for an exothermic reaction. So we have this reaction between the reactants and the product. So energy of the product is much lower than the energy of the reactants. You can see there. Reactant has energy about that amount, okay, up to there, but the products it has a much lower energy. Now, the reaction is if the reaction wants to go forward, it has to go this way, okay, and activation energy, okay, this is activation energy. Okay, this is energy of the reactants, and this is the activation energy from here to here. Okay, and this is the activation energy with the catalyst. So with the catalyst, the activation energy is much lower. This expected that the energy is much lower. Okay, no energy release, net energy released by the reaction. This is the amount, this is the net amount of energy which is released by the reaction. In the presence of a catalyst, the reaction is complete in a few seconds. For example, we have PCl3, phosphorus trichloride, reacting with a sulfur to form phosphorus sulfur trichloride. In a few seconds, okay, we have already formed PSCl3, phosphorus sulfide chloride. Okay, because we have added some catalyst in the reaction mixture. The lab preparation of oxygen uses manganese dioxide as a catalyst to increase the rate of the reaction. And here we have potassium chlorate, okay, and we add manganese dioxide to the reaction so that we have the formation of KCl, potassium chloride, and also oxygen. Now, this is a method to produce oxygen, okay, in the lab, and we can use manganese dioxide, okay, to accelerate or to expedite the process. Let's see this example equation, okay, how to calculate calculation equation. The equilibrium constant K has a value of zero point 0.3. Assume zero point 0.3 of A and zero point 0.5 of B are dissolved in 1 liter of solution and the reaction proceeds. Calculate the concentration of reactants and products at equilibrium. Okay, now how to solve this kind of problem? We know that A and B reacting to form C and D. So we have KEQ equals to concentration of C times concentration of D over concentration of A and B. Okay, so solution is try to build a table. Okay, the first row is the initial. We have change of x, and we have equilibrium. Now that's the first column. The second column is concentration of A, concentration of B is the second column. So the third column, the fourth column is concentration of C, and the fifth column is concentration of D. For every reactant and products, which is A, B, C, and D, at initial stage, it was given in the problem that the number of moles of A is zero point 0.2, number of moles of B is zero point 0.5. Now, we need to know the concentration. So, zero point 0.2 over 1 liter. So, zero point 0.2 over 1, which is equals to zero point 0.2. That is the value for the concentration of A. The value of concentration for B is zero point 0.5 over 1 liter, which is equals to zero point 0.5. So at equilibrium before the react, okay, sorry, or initially we have zero point 0.2, concentration of A is zero point 0.2, concentration of B is zero point 0.5, and the concentration of C is 0, D also 0. At change, okay, we have decreasing amount of x minus x. Okay, for A. For B also minus x. For C we have increasing plus x, and for D we have also plus x. At equilibrium we have zero point 0.2 minus x for A. For B we have zero point 0.5 minus x. For C we have plus x also. Okay, and for D we have plus x. Now K equals to zero point 0.3. So we insert the value at equilibrium here into this equation. Kq equals to concentration of C times concentration of D over concentration of A times concentration of B, which is equals to x, this x and this x over zero point 0.2 minus x times zero point 0.5 minus x, which is equals to zero point 0.3. Now let's open up that quadratic equation. We have 0.7 x squared plus 0.21 x minus 0.03 equals to 0. Now we can solve for the x value. Okay, using this equation, s equals to minus b plus minus square root of b squared minus 4ac over 2a. And if we insert the value there, we have the value for x as 0.11 m. Concentration is mole per dm cube, right? Or mole per liter. Now, concentration of A equals to, let me try to increase this. Concentration of A equals to zero point 0.2 minus 0 minus x. So it becomes zero point 0.2 minus 0.11, which is equal to 0.09. For B, zero point 0.5 minus x, which is zero point 0.5 minus 0.11, that becomes 0.39. C and D is x, so it's 0.11 m. Okay, so that answer the question given. Okay, thank you very much. I hope you enjoy the session. Okay, you can ask me any question. Okay, thank you and assalamu alaikum.